Good afternoon, friends. Welcome to this lecture 14 on neutrons as probe. Professor S.M. Yusuf is starting the module on magnetic neutron scattering. This is the most interesting and possibly the most demanded topic in neutron scattering. And Professor Yusuf and his group has been working on this field for a long time, and I'm sure you will learn a lot from this talk. I'm sorry for this delay. Without any further making you wait, I will invite Professor Yusuf to deliver his lecture.
First of all, I'd like to thank Professor Sohaibul Basu for organizing this course module, and thank you. I also thank him for I also thank him for giving me this opportunity to deliver this series of lectures. And as he already pointed out, that neutrons are very, very powerful to study magnetic materials, to study magnetism. And this is what is the subtopic from this course on Neutron as a probe of condensed matter. So now you will be going through a tour where you will see how neutrons are useful for studying magnetic materials and magnetic properties. So far from the course module, I have seen that you have gone through all the basic properties of neutrons. And now today, I'll start, as I said, the magnetic neutron scattering. And lectures are scheduled such a way that today's talk would be more on the application of neutrons, because my intention is to create some kind of interest that why neutrons are useful, why one has to use neutron for studying magnetic materials, for studying magnetism. If you use neutrons for magnetic scattering, ultimately, end of the day, what you get, what you learn out of it, what is the utility of this. So this is what, so in other words, today's my talk would be partly on the research topics, and I am sure many of you are working in the area of magnetism and magnetic material, so you will definitely appreciate it. But so today's talk would be at least 50 to 60% would be on the application of neutrons on magnetic materials, and you will see that what you get by using neutron as a fundamental probe for studying magnetic materials in the area of condensed matter physics. But of course, my next talk would be more on elementary aspects of neutron scattering involving magnetism. So that means how the magnetic scattering takes place, what is the basic interaction, what is the basic fundamental aspects behind this magnetic scattering. So that will be more elementary, that is next lecture. But today I want to make some kind of a point that yes, indeed, neutron is an excellent probe for studying magnetic materials, and you all must come forward for that. So with this introduction, let me start from elementary stuff that when you talk about magnetic materials, what do you understand by that? See, how do we get magnetism? As you know, that when you consider an atom, of course, you have the nucleus sitting at the center, and you have these electrons in their orbits. And if you look at the periodic table, and there are certain elements, a group of elements, where you will find some electronic shell where this spin pairing is not fulfilled. So it means there are unpaired electrons. And if that is the case, so you will find the 3D tensile metals, iron, cobalt, nickel, manganese, they are from the 3D. So if you consider these elements in the periodic table, what you will find that at the 3D electronic shell, there are unpaired electrons. For example, what I have shown here, the nickel, where the Z, the atomic number is 28, and suppose you are considering Ni2 plus, why are you considering Ni2 plus? Because you can have the nickel-based oxide, for example, NiO. So you know oxygen is 2 minus. So the nickel will be in 2 plus. So that's why 2 plus is relevant for the discussion. And if you see the electronic configuration, it will come like this, 3d8. And in 3d8, d state, there will be 8 electrons. And those 8 electrons will be distributed like this. First, as you know, as per the Hund's rule, and I must remind you that Hund's rule is applicable for an isolated atom or ion. Okay, so that means as if nickel 2 plus is a bare ion, and that means under no influence of any crystalline field or magnetic field or any kind of perturbation, under that scenario, the Hund's rule is applicable. And what you say that 8 electrons you will be putting first to maximize the spin. The ultimate requirement is to have the lowest energetically ground state. So first 1 up, second up, third up, and fourth and fifth. But then you have 8, so you could only accommodate this 5. So remaining 6th one has to go down, spin pairing, 7, and 6th one will also go down. Similarly, this one will also go down. So finally, you will have 2 unpaired electrons. Okay, these 2 unpaired electrons are responsible for this magnetic moment. So spin pairing, wherever it is not possible, not there, that causes this non-zero moment. Okay, and so this is all you know. So similarly for the 4f element, that is Riemann series, if you go across the Riemann series, you will end up getting these unpaired electrons at the 4f shell. Similarly for actinides, uranium, for example, you will get unpaired electrons at the 5f shell. And you can also have magnetic elements or magnetism out of 4d, 5d. For example, ruthenium, rhenium, and so on. You might have come across the magnetism in so-called molecule-based magnetic materials, where even you do not need any so-called this conventional magnetic element like 3d or 4f or 5f or even 4d or 5d, but you can have magnetism based on s and p orbitals. So these are the root cause of this elemental, if you talk about one atom or ion, how the magnetic moment comes. You have S and you have L and you can have J total. But of course, I must tell you that when you put this atom or ion in a material, in a let us say environment where there are other atoms or ions, then this Hund's rule may not be applicable, and I will come across some situations. So as I already said, this for actinides, this 5f shell is responsible where you have unpaired electrons. For example, uranium 92, I have shown it, and for rare earth, it is 4f shell, and 3d it is the 3d shell, tensor metals. Now, that means once you have this non-zero magnetic moment for an atom and ion, so pictorially you can represent like this. This is my atom or an ion. Okay. So the electronic moment I am showing by this vector arrow. Now, if you have group of atoms, for example, in experimental scenario, you are doing experiment, let us say using 100 milligrams of sample. So you can imagine how many atoms are there. Of course, you are counting only magnetic atoms, and that means we have the atoms. The sample is made of some atoms or ions, which, as per the Hund's rule, gives you non-zero L or S or non-zero J. So that's why you have this vector. Now, if you keep this group of magnetic atoms in a temperature bath, which is relatively, let us say, higher, I'll qualify this statement. What do you mean by relatively higher? So at a given temperature, let us say all these moments are randomly oriented. Means what do you mean by randomly oriented? There is no correlation, orientational correlation of these vectors. Okay, and also if you took so between two moments, there is no orientational correlation. Means they are totally decoupled. Then and if you see only one particular magnetic atom or ion as a function of time, then also you see this direction is at t equal to 0, let us say along this, and t equal to t1 maybe along this, t equal to t3 maybe along this. So means the self correlation is also 0. So this is what is called truly random system, where the self-correlation is zero, as well as the correlation between ith and jth moment spins, they are also non-zero, zero. So in that case, truly disordered system, and that is called the paramagnetic system. And paramagnetic system, as you know, if one calculates magnetization, you get this kind of famous equation involving the Brillouin function. Of course, this is where you see the J is the total magnetic moment, that means the L plus S, and this is a true paramagnetic case, and this is the quantum mechanical origin. You know the derivation, you can see Askov and Mermin, but of course, if J is very large, it can boils down to the Lange equation, that means J is very, very large. So I will not go in that direction. So that means this is a true disordered state at a given temperature, but there is no correlation. So that is we call the disordered magnetic state. That means it is known as paramagnetic state. Okay. Now, so this is what is my disordered state. I already introduced that the interaction between these two magnetic moments, what I said, if it is there or not there, that is the question. Now, if I denote that the interaction strength as Jij, now effective interaction strength here, as you see, not there, that side is disordered state, that side is paramagnetic state. Now, if you lower this temperature, that means if you lower the temperature, below certain temperature, is moment orientations could be quite regular. So, when this kind of regular orientation of these vectors, so it is called ordered state. Here we are talking about magnetically ordered state. So far, I have not talked anything about the this atomic position. These are all atomic representation. How the atoms are arranged, that I have not talked about. It means you can deal with crystalline material, you can deal with disordered amorphous materials, so on. But with regard to magnetic moment orientation, this is the ordered state because there is a definite orientation. That means there is a definite correlation, orientational correlation between any two magnetic moments. So, so this is what is the ordered state. And when do you get this? At a sufficiently lower temperature. Now, what do you mean by lower temperature? Here we are talking about two kinds of energies. One is the at a temperature bath, say it is the temperature of this bath where you have kept this your sample, and then corresponding energy is kBT, the thermal energy. So kBT is the thermal energy, which is a disrupting energy, which will try to destroy, any kind of regular orientation. That means that will try to, kBT is responsible for the disordered arrangements, disordered orientation of these moments, whereas the something that is Gij, which is the interaction, magnetic interaction, and very precisely magnetic exchange interaction, that will try to keep them aligned in a particular way. So it is a competition between these two, disrupting energy kBT, thermal energy, versus this exchange energy Gij. So it is a matter of case which one wins over. If Gij is higher than, greater than this kBT, then you get this state. If Gij is less than the kBT, then this disordered state is there. So that's why at higher temperature, you invariably get this disordered state, paramagnetic state, and as you lower the temperature, at certain temperature, when these two energies, kBT and Gij, becomes equal, so that is the temperature where the phase transition takes place from the disordered state to ordered state, and we call it magnetic phase transition. And below that temperature, Gij is effectively stronger, so you get this state. I must clarify at this point, even in the so-called disordered state, paramagnetic state, Gij is never zero. Gij is always there. As long as these magnetic moments are there, these are called dipole moments. And as I already said, origin is the Hund's rule, essentially. So as long as they are there, there is a exchange interaction. So this is never zero, but it is a question of which wins over. Okay. So in paramagnetic state also, Gij is never zero, but kBT takes over. So now, as I introduced that so-called magnetic ordering, so then when we talk about magnetic ordering, the regular arrangements of magnetic moments, okay, or spins, then how do you quantify? Of course, you can measure certain physical quantity. For example, specific heat, one physical quantity. This spontaneous magnetization is another physical quantity. For example, if you measure spontaneous magnetization and if you come from higher temperature, you see this. I am plotting kBT by J. So this is the same J, you know. So kBT by J higher means this is the higher temperature. That means above this temperature, so-called the spontaneous magnetization is zero. By the way, this when we say spontaneous magnetization, it is not the atomic. It is here. If you have to go a little deeper, it is the concept is already built in. This is the arising out of the entire system, like a cooperative phenomena. Like you already know about magnetic domains and this kind of situation. Means when you cool the specimen at this particular temperature, your spontaneous magnetization builds up. So magnetic ordering takes place, and then this order parameter, this you can call magnetic order parameter, it just builds up from 0 to this value, and then obviously at lower temperature it saturates. So order parameter is 1, fully ordered. But if you do the specific heat measurement, so this is another thermodynamic quantity you can measure. So as a function of temperature, if you do, what you see at from higher temperature, as it approaches towards so-called this magnetic order temperature, it diverges. It diverges. So this is what is the diverging. And this is the experimental scenario. Theoretically, of course, what is you will get only delta function. You don't get any points. But when you do experiment, you do get points. That is for the experimental scenario. And basically, essentially, there is a divergence of this physical quantity specific heat at the tension temperature. So this is called phase transition. Now, I introduce that something called the exchange interaction between these magnetic moments. Now, what kind of interactions I am talking about? Say, if you go back to the classical theory, once you have the two, let us say, if you take two bar magnets physically, the big, large bar magnets, chunk of bar magnets, you know, this big. So they will interact. And you know what is the interaction called? That is called dipolar interaction. That is a classical one, okay? So once you have two magnetic moments, they will interact, and that is called classical dipolar interaction. Of course, that is always there, whether you have a giant bar magnet or you have atomic dipole moments, that is always there. Now the question is, in our day-to-day life, if we play with two magnets, bar magnets, what we come across, what we talk about, though they are physically maybe 20 centimeter apart, 5 centimeter apart, we do see the magnet is attracting each other. There we deal with the classical dipole-dipole interaction, okay? That was known long back. But when you come to this so-called, the microscopic theory of magnetism, so-called the atomic moment alignment in a crystalline material, or, you know, that kind of scenario, when you talk about the atoms are separated by, the atom means magnetic dipole moments are separated over 1 or 2 angstrom length scale, that kind of scenario, what I am talking about, and we are dealing with only atomic magnetic moment or ionic magnetic moment, which is very tiny, because as I said, it is arising out of those unpaired electrons at the 3d or 4f cell, and each unpaired electron gives you 1 Bohr magneton. So we are talking about that kind of unit, 1 or 2, or manganese, let us say 3 plus 1, 2, 4, 5 Bohr magneton kind of dipole moment we are talking about. So with that kind of dipole moment strength, what is, of course, classical dipole-dipole interaction in principle always there, but that strength is very negligible. And one can do this calculation. You can go back to your Kittel book, and you can see that if you do that calculation, so that interaction will be very small. So how do you translate? If J is very small, so that means if you have to get magnetic ordering out of only the classical dipole-dipole interaction, then magnetic ordering cannot be typically above 1 Kelvin. But in real life, you know, for example, if you take a piece of iron, even at room temperature, it is ferromagnet, okay? In fact, 1083 Kelvin is the QD temperature, magnetic ordering temperature for BCC iron. That means experimentally what you see in real life, that magnetic ordering temperature can be very high, very high. So that means the classical dipole interaction cannot explain this real life fact that you get a magnetic material where magnetic ordering temperature is very high, and which cannot be explained due to the classical dipolar interaction. Otherwise, all materials should have ordered, if at all, only below 1 Kelvin, because strength is so weak. In other words, that thermal energy will be always winning over above 1 Kelvin. So that's why, as you know, historically, the quantum mechanical X interaction had to come in, and the very first one, as you know, the direct X interaction, which was given by Heisenberg. So Heisenberg in 1924, he proposed this direct X interaction, and you know that you can again go back. I'll just in my next slide I'll give you the expression for that. So this is where it takes place when there is two orbitals. Let us say one you have 3D atomic 3D ion, another 3D ion, typically separated, let us say 1.5 angstrom, that kind of scenario. So 3D shell has a typical physical extension, physical size is about 1 angstrom kind of. So they are separated by 1.5. So there is a direct overlap between one 3D cell and another 3D cell. So there you can expect this kind of direct X interaction. There are other kind of X interactions are possible. For example, super exchange, indirect exchange, double exchange, Archequois exchange, and Jalasinski-Mori interaction. So I must tell you that only 7 is the classical one. All this 1 to 6, they are all 1 to 6, they are all the quantum mechanical in origin. All quantum mechanical origin. Super exchange, for example, takes place when you have two magnetic atoms, you have intervening oxygen or like that. Okay. Archequois, it takes place via these conduction electrons between, let us say, you have two rare earth magnetic ions and they are far apart, but you have a material is conducting. So via the conduction electron, this Archequois X interaction can take place. So I give typical example, the direct X interaction. As I said, two orbitals, they are overlapping, and this is the Heisenberg X interaction, JID SI dot SJ. And for example, nickel, cobalt, manganese, they can have this kind of positive X interaction. So that leads to ferromagnetism. And in manganese case, this X interaction is negative between two. So that's why pure manganese, these are our elemental I'm talking about. So elemental nickel, elemental cobalt, elemental iron, they are ferromagnetic due to this positive X interaction. And this elemental manganese is antiferromagnetic due to negative X interaction. J is negative. And if you have the direct X interaction. So one thing I must tell you, once you talk about this X interaction, you are no longer talking about that isolated atom or ion picture. So you are deviated from the so-called Hund's rule. That means you are already talking about cooperative mechanism. So magnetism is nothing but cooperative mechanism. This is due to the Avogadro number of atoms, magnetic atoms, they are magnetically interacting through this GIJ, what I just said. So that's why magnetism, superconductivity, all these ferroelectricity, all these properties are it is not an isolated atom or ionic picture. It is the cooperative mechanism, cooperative phenomena what you come across. As I said, super X interaction, another quantum mechanical origin. You have one 3D magnetic ion, another 3D you have between oxygen. So if oxygen p sigma orbital or p pi orbital, depending upon that, you can have these X interactions, either positive or negative, either ferromagnetic or antiferromagnetic. As I said, Archequois X interaction between two moments, it can interact via the conduction electrons, and you see this oscillation. Okay, this Archequois can be oscillative type. It can be positive or it can be negative. Also, it is a function of separation between two magnetic atoms R. So either at what distance they are separated, they are located. Suppose separation distance is such that it is lying here, R is here, so it will be positive. But if the separation distance is here, then it will be negative. That means they will be antiferromagnetical aligned, antiparallel aligned. But here moment will be parallel aligned. So this is what is beautiful thing. Now, when there is phase transition, as I said, so higher temperature is the disorder paramagnetic state, and you come to the lower temperature, and this is called the ordered state. And there are different kinds of magnetic ordered state possible. I have listed some of these, and you know, ferromagnetic, ferrimagnetic, antiferromagnetic. Magnetic structure could be very, very complex. So that is what today's lecture, what I proposed already, that I will be talking about. I will be showing that how neutron can be fruitfully utilized for determining magnetic structures. And so today's talk will be more on towards that direction, and the next talk will be more on fundamental, because I need to generate interest that why do we bother about neutron magnetic scattering at all? What does it give us at the end of the day if we do magnetic neutron scattering? Again, little bit. There's a little bit, okay, see, the magnetic phase transition, when we talk about the order of the phase transition, it can be, that is defined, if it is nth order phase transition, so means nth derivative of free energy is discontinuous, but n minus 1th derivative is continuous. So there is a little problem in this matching, because different version of this PPT. Okay. So phase transition, why I'm saying so, I just talk about the order state to disorder state to ordered state transition. So this could be of different types. There can be different first order phase transition, second order phase transition. But invariably, I must tell you, most of the invariably, quite often you see magnetic transitions of second order in nature. Okay. But of course, there are few cases where you can have first order magnetic phase transition. So the order of the phase transition depends upon the derivative of the free energy. If nth derivative is discontinuous, n minus 1th derivative is continuous, then it is called nth order phase transition. Now, again, that magnetism, we must know that why magnetism is so important in our life. Just one second. Is it possible to put it up? Yeah. Okay. So magnetism is I want to give you a historical perspective that, in 13th century BC, the Chinese used this compass, and that was the starting, some kind of discovery of a magnetic material in practical applications. 600 BC, say Greek, they discovered the Fe3O4, that that is known as magnetite. Fe3O4, that is attracting iron pieces, so action of magnetic force. Then 1600, you see that discovery of static electricity and Earth's magnetism. 1819, the worsted came, and the worsted is the unit of magnetic field. Gray discovered the electricity and magnetism relationship. Then, of course, around 1820s, Faraday, Henry, Maxwell, and your whole of electrodynamics. Okay, Jackson, you have read, right? J.D. Jackson. This is based on this electric field, how it depends on the magnetic induction, and magnetic induction, how it depends on the electric field. So this is all about. And then 1960s, you see the invention of DC motors and generator. Then if you keep going, 1880s, you see the Kirchhoff's law, Coulomb's law, alternating current, and so on. 1910s, you have commercial steel magnets. So steel magnet commercially produced around this 1910. Then Alnico magnets, more powerful magnet around 1930s. Around 1950s, you see the ceramic magnets, hard disk drives. So this is the birth of this computer storage devices. Okay, so it is linked to this computer utility around 1950s. Then 1960s, more powerful magnets are made, rare earth-based magnets, and it is very much related to these computers. So our availability of computer is very much coupled with the availability of magnetic storage devices that you can see. So in 1980s, there are other discoveries like ND2 Fe14, boron-based. These are more powerful magnets. Then there are some magnetic phenomena that discovered like quantum Hall effect, then GMR, giant magnetoresistance, TMR, tunneling magnetoresistance, these effects, which, the GMR got Nobel Prize and so on. Quantum Hall effect also got Nobel Prize. So this kind of discoveries in 1980s. And as far as I am concerned, I started my research career in 1989. So you see the time scale. Then if you further keep going, in 1970s, little earlier, 1970s, the low dimensional magnetism, another discovery called magnetocaloric effect. And there are basically magnetic phenomena, and they're important in their own rights, fundamentally as well as application point of view. 1990s, you see the molecular magnetism, magnetic drag delivery, quantum magnetism, colossal magnetoresistance. So this is one, very fantastic discovery. The resistivity of a material is dependent on magnetic field, and when the change of the electrical resistance on a magnetic field very huge, that is called colossal magnetoresistance effect. You go to around this early of this century, that is 2000s around, discovery of multiferroics. That means two ferroic properties, that is ferroelectricity and ferromagnetism or antiferromagnetism. Whether can they appear in a given material simultaneously? So two ferroic properties, more than two ferroic properties, multiferroic. Another discovery, diluted magnetic semiconductors. See, semiconductor industry, but if one can have the magnetic semiconductor, then in semiconductor, what is exploited? Electronic charge, right? But if you have magnetic semiconductor, besides the electronic charge, you will be also exploiting the electronic spin. So you have more handling parameter so semiconductor industry will be altogether different. But the question is how to get magnetic semiconductors which will show semiconducting properties as well as magnetic properties at room temperature. That is the challenge. Okay. Then around 2008, another discovery called, the Seebeck effect, Peltier effect, Seebeck effect, but spin-based Seebeck effect. So this kind of, you see that how these various magnetic phenomena, magnetic materials are discovered with time. In our group, in Bhabha Atomic Research Center, we have been working on various kinds of magnetic materials. Some are of more fundamental side, for example, one-dimensional magnetic material, two-dimensional magnetic material, quantum magnetic materials. Okay, so what is understood by 1D and 2D? Because conventional materials are three-dimensional. You take any block, it is you have X, Y, Z, right? But if you have a system where the magnetic atoms are only along the chain or magnetic atoms are in the plane, so then you get 1D or 2D. Quantum magnetism is very, very hot topic because the quantum at t equal to 0, quantum fluctuation is the driving force in such materials for any magnetic phase transition. So quantum property, different phase transitions, multiferric materials we are working, molecular magnetic materials we are heavily working on, nanostructure magnetic materials, spintonics materials. Recently we have started working on battery materials, and of course the material which show large magnetocaloric effect. Caloric effect, when it is shown that caloric effect is dependent on magnetism, then it is called magnetocaloric effect, and you need to have large effect for practical applications. We have, this is what I, now slowly you will see that I am bringing neutron, okay. As you know, to study magnetism, there are many, many other techniques, bulk techniques. For example, DC magnetization is the very novel technique for studying any magnetic material. Of course, we do all those, but then for microscopic understanding, mesoscopic understanding, means atomic length scale what is happening, or domain length scale what is happening, you need to use neutrons. And we have been using this. Our facility I will be showing at the Dhuba Research Reactor in Bhabha Atomic Research Center, Mumbai. And there is a unique facility, only neutron scattering facility in India, as you know, because other places are no research reactors. This is under DAE, Department of Atomic Energy, and we have been working. This is one of the recent review. What we wrote, the neutron scattering of advanced magnetic material. This review I wrote with my colleague, Dr. Amit Kumar. You can see some of the cases we have discussed here in Applied Physics Review. Now, a little bit history. When I am talking about the use of neutrons in studying magnetic materials, we must briefly review how we came into this domain, how we came into this use of application of neutron in magnetic materials and so on. See, as you know, neutron was discovered by Chadwick in the year 1932, and 1932 neutron discovered. So that is what you understand. And as I already told you that the Heisenberg exchange interaction was discovered in 1924 or so. So you see the timing. Now, due to this discovery of neutron, this in just 3 years' time, this Chadwick got the Nobel Prize. And you know, in that time, neutron was just discovered. Neutrons were not used for any applications, but the Nobel citation is like this. This is what you have to appreciate, how they could foresee what should be the use of neutron, rather how Chadwick could foresee that the neutron discovered by Chadwick has here given a powerful instrument for future researchers on the structure of atoms and molecules. So this is what is the part of the Nobel citation, which was in Chadwick's discovery of neutron in 1932 and followed by 1935. And you see that the actual utilization of neutron came much later. I'm going to that. How do we get neutrons? Okay, in our for our experimental purpose, for example, in a reactor, what we do, we bombard. To start with, we get a neutron from other source, and then we bombard. Let us say 1 neutron. If you bombard an uranium-235 nucleus, then the fission takes place, and on the average, 1 neutron gives you about 2.5 neutrons. Means here I am showing 3. In some cases, it is statistically 2, sometimes 3, and so on. So on the average, of course, the fission fragments are there, and this is the most popular, but there is always a distribution. So essentially, what I'm saying, the neutrons you can get out of the fission of this heavy element uranium-235, and you get neutrons. So these neutrons can be used for carrying out neutron scattering experiments. In fact, indeed, we do that in our reactor source. And of course, these neutrons also can be used for nuclear weapon purpose. I mean, so it is a question of whether we talk about this. This is called chain reaction. If you start with 1 neutron, you get 2.5 neutrons. So that means it is a self-sustained, this nuclear reaction is possible, fission is possible. So that's why it's called chain. Once you start, it will keep going. Now the question is, why this chain reaction, is it under control or not control? In a reactor, it is very much under control. That's why we are able to do experiment there. Nothing happens. But when it is used as the nuclear bomb, the nuclear weapon, of course, it is not controlled. It explodes, as you know. And Pokhran test, you all remember in this regard. Or you also remember that what happened in Hiroshima and Nagasaki, in Japan, okay, with regard to the World War. So in that context, I must tell you, the first research reactor was built in Oak Ridge National Lab, that is known as the graphite reactor. And in the graphite reactor, if you see the graphite reactor, and so that was, of course, famous, that is famous because there where the first nuclear bomb was made and so on. You can read the history, all are available. But at the mezzanine floor of that, there is a small room. In fact, I have visited there. See, what you see here is a small instrument which was built. This is the first first neutron diffractometer. You know, you have done X-ray diffraction, X-ray diffractometer, which is more compact. But this is a picture of the neutron diffractometer. And what you see in this picture, this two gentlemen who is standing is Professor C.G. Schall, and who is sitting here, this Professor Olan. So Professor Olan did PhD under Professor Schall. So Professor Olan is the student and he's the professor. Okay, they are doing experiment, and they did that historically in 1950. They carried out the experiment, and you know that MNO, this experiment they carried out, and MNO is antiparamagnetic. That was the first direct experimental evidence that what is the meaning of antiparamagnetism. You know, how the moments are aligned in case of antiparamagnetism. So Newton could only reveal that mystery, and that finally led to the gave them this Nobel Prize, and that came in the year 1994. Of course, the Nobel Prize was shared by another gentleman, Professor Brookhouse. He worked on the dynamics aspects of the neutron scattering, and Professor Schall, he works on the structural aspect, particularly the magnetic diffraction aspect. But here I must tell you, the student is doing the experiment, and you see the guide professor is standing with a notebook. And when Nobel Prize was given, it was given to professor, not to the student. Okay, don't be disheartened by this. Okay, because student also becomes professor one day. Then what happens with time? This neutron sources are built. That was the very first one, which I told you. This one, X10. This is the graphite reactor at Ogre National Lab. Then with time, many reactors are built. In fact, our reactor, dhuba research reactor, flux-wise it is 10 to the 14, 1.5. So it will come here, and it was built in 1985. You know, so time scale is here, and flux-wise this is it is here. Okay, so this is called a reactor-based source. And at present, you know, the ILL, Institut L'Islande at Grenoble, France. It is a very powerful, the steady-state research reactor, and we all keep going there for experiments. But of course, the neutrons can be also produced from this spallation neutron source. So there are many such, and you know this. If a Chinese spallation neutron source is already giving the beam, this is the ISIS one, where India has through DST means we have the access to the ISIS at Rutherford Appleton Laboratory, UK, and this is the SNS at Ogre National Lab, and so this is the in PSI, SynQ, and so on. So this is this kind of neutron flux we deal with. Here you must see that these many neutrons, 10 to the power 15 neutrons per square centimeter per second. So if you compare this neutron flux with regard to your X-ray X-ray photons, what you get from even lab-based X-ray source. So you can imagine how weak it is compared to the X-ray. If you go to synchrotron, then you get much better X-ray flux, photon flux. So here I would like to only make the point, when you are trying to do neutron scattering, so penalty is that flux is less, even if you go to the world-based source. So penalty is that you have to carry good amount of sample volume, the scatterers, number of scatterers, which gives you the signal. Signal has to be measurable, you know, sufficiently measurable. So that is possible only when you use more number of scatterers, means your sample quantity is more. So that is what is one point we have already learned, I am sure. Coming back to Indian scenario, this in India Atom Energy Commission was set up 10th of August 1948. Just see the timing, and you know the role of Homi Jahangir Bhabha, who is the now we are in DAE, so you know the role of Professor Bhabha. And it was set in this Indian Atom Energy Commission was established in the year 1948, 1947 when we got the freedom. So just within 1 year. So you see the timing means how advanced we are in terms of this atom energy program. Thanks to Professor Bhabha. And then of course this Atom Energy Commission formally was formed on 1st March 1958. Presently it is under the Department of Atomic Energy, and I'm fortunate to be under DAE. So this is what I will not go too much on the history, but just to give 1 or 2 slides. Here you see the first research reactor was built in Bhabha Atomic Center, Mumbai, where I am from. And this Pandit Jawaharlal Nehru is inaugurating this. It is the Apsara, as you see, and the year you see 1957. Then this is another research reactor, Cyrus, again in Bhabha Atomic Center, and you see Homi Jahangir Bhabha is standing here with kin near the instrument. And the present view graph of Bhabha Atomic Center is like this. And at present we have this reactor, which is indigenously built. This is the dhuba research reactor, and our facilities are located here. And we carry out experiments in this lab. And it is the picture inside the dhuba reactor. So some of you might have visited by now. And this is the pictures of some of the instruments here. But what I would like to tell you, basically this is the reactor core. So there are channels, open channels basically. So neutrons come out. As I said already, that due to nuclear fission of uranium-235, the chain reaction takes place and the neutrons are produced. Of course, neutrons are produced with mega electron volt energy because these are nuclear fission. But those mega electron volt energy, they are reduced to milli electron volt energy. This, I am sure this has already been taught to you by Professor Soibal Basu. That is called moderating the neutron. That is nothing but the inelastic process through which you reduce the energy of neutron from mega electron volt to milli electron volt, and those milli electron volt neutrons, they come out from this reactor through these beam holes, and you set up different experimental facilities all around. And you already know why do you need milli electron volt energy? Because milli electron volt neutron energy corresponding, if you calculate de Broglie wavelength, lambda equal to h by p, you will end up getting lambda is typically 1 to 1.5 angstrom. So that is what is the requirement. Why? Because we are interested in studying materials. We are interested in studying materials, where material typically, whether it is crystalline or not, typical atom-atom separation is 1 angstrom. So we need a probe. We need a probe which can measure that kind of length scale. So atomic separation length scale, planar separation length scale. That's why we need milli electron volt kind of time scale. Okay, and also that milli electron volt energy is also suitable for measuring magnetic excitations. Okay, and also the neutrons. So this is the pictures I am showing of some of the neutron instruments, particularly for neutron diffraction point of view. They are there. So these are, I'll be showing neutrons some results based on these facilities. As I said, out of this reactor, you are getting neutron flux, which is having, of course, distribution and having maxillary distribution, and typical the peaking here around 30 milli-electron volt. So lambda wise, so 1 to 1.8 angstrom kind of neutron we are talking about. Okay, on the average 2.3 neutron comes out from each fission, and this is already talked about. Now for magnetic materials, this is my point. Neutron has magnetic moment that is minus 1.913 nuclear magneton. Mind it, this is not Bohr magneton, this is nuclear magneton. In other words, neutron mass comes here. So neutron mass is typically 1800 times, so this 1800 times weaker, this because neutron mass comes. So that is what you see the nuclear magneton here. So that means it is a very, very tiny magnetic moment compared to the electromagnetic moment. Okay, but so this tiny neutron magnetic moment, it is a magnetic dipole. So neutron is nothing but a magnetic dipole. So this is one magnetic dipole, and neutron is chargeless, so it penetrates deep into the matter. Let us say you have a magnetic material, let us say you have a iron-based magnetic compound, so you put in the neutron beam, so neutron goes inside because it is a chargeless, unlike X-ray, so deep into the matter, and it sees every magnetic atom by atom. And so the neutron magnetic moment interacts with those electronic magnetic moment if there is there. Means if you deal with magnetic sample, then this will interact, okay? And that is the root cause of this magnetic scattering. So in other words, we are exploiting this property, the neutron magnetic moment property. We are exploiting it. Now what I do, of course I have many examples, but depending on the time, I'll stop at any point so that next day I can continue. I will be giving some examples that from here, without elaborating too much on the physics part, that why we study that kind of material, why do we study that kind of magnetic material, but rather I will try to show if you use neutron scattering on this kind of material, magnetic material, what you get. And obviously what we get, it not only gives you the fundamental understanding about magnetism, but there are practical implications. And I have already given you the discovery of all magnetic phenomena, major magnetic phenomena discovery over the century. So Newton has played very, very important role for that. Now, if I take one example, already I introduced the magnetic phase transition, the disordered state to ordered state, let us say paramagnetic to ferromagnetic. If I take that kind of material, so if I use Newton, what I get out of it? You know, if you take a so-called ferromagnetic material, if you do magnetization measurement, DC magnetization measurement as a function of field at a particular temperature, you may get typically this kind of so-called curve, okay? If you enlarge it, you may get hysteresis. So this is a typical ferromagnetic kind of system where there is a almost like a saturation. If you do susceptibility, plot 1 upon chi versus t, and you know that so-called Curie-Weiss law, as a function, so you know reciprocal susceptibility, it gives a straight line, but this straight line it deviates here, okay? So that means this is the temperature where T equal to theta, where this phase transition taking place. And below this temperature, susceptibility is not defined, rather you get this kind of DC magnetization curve. Now, if you take this kind of, if you do DC magnetization, you get this, but you do not get any microscopic understanding. What I mean by that, you do not get to know how much is the moment attached to one individual magnetic atoms. In this, for example, this compound, where do you see iron is magnetic, carbon, nitrogen, water, they are non-magnetic, okay? Iron is because there is 3D electron shell where unpaired electrons are there, as I already told you. So these are the magnetic elements. But from this DC magnetization, you get to know the bulk property as a whole. As a whole, how much is magnetization, EMU per gram or Bohr magneton per formula unit, and so on. Okay? So I want to know a little bit on microscopic length scale what is happening. So for that, what do we do? We carry out neutron diffraction experiment. What is that? It is similar to X-ray diffraction. As a neutron beam falls and it gets scattered, and you measure the scattering angle. As a function of scattering angle, measure the scattered neutron intensity. So as I said in my next lecture, I'll be covering more on that aspect, what actually happens, interaction process and so on. Today I'll try to motivate you what is the use of using neutron on magnetic material. If you do that at a temperature, let us say 50 K, so this is this kind of Bragg peaks you get, H-scale peaks are shown here, but here so-called it is the, but if you lower the temperature, let us say you go to 1.5 Kelvin, you see the intensity is increasing. But at the same position where you have the Bragg peaks, you know. So that means you do not get any additional magnetic Bragg peak, but you get additional intensity when you lower the temperature. And so this is the signature of a ferromagnetic ferromagnetic ordering, because ferro or ferrimagnetic also gives this similar without giving any additional Bragg peak, because magnetic symmetry and the crystal symmetry, they are same. So this does not lead to any extra Bragg peaks, rather it leads to only enhancement of intensity due to magnetic ordering, due to magnetic phase transition from paramagnetic state to the ordered state. Now, if you draw microscopic picture, so we will be drawing this kind of picture. So what is this picture? Let me tell you. This is the system. This is the system. Now, here iron atom is sitting here, one iron atom. Another is here. In between this iron atom, if you see, this is one nitrogen. This is another nitrogen. Similarly, you have this side nitrogen, this side nitrogen, this side nitrogen. So if you see the three-dimensional picture, iron 1 is surrounded by nitrogen octahedra. Similarly, another iron, this is at 000 position with regard to this unit cell. Unit cell is the building block of, this is called magnetic unit cell. So this is the building block of magnetic domain. Okay. So let me tell you point by point. This is one magnetic atom. Okay. Then these magnetic atoms with this non-magnetic, this is one called building block, that is magnetic unit cell. And if you repeat this cell in all three directions, so what you get? One magnetic domain. And this unit cell typical size, it is about, this is about 4 to 5 angstrom, this, this length scale. So you can see the unit cell size. Typically 4 to 5 angstrom is lattice constant here. And if you keep on adding these unit cells, you get one magnetic domain. A magnetic domain size is typically micron. 1 micrometer is 10,000 angstrom. So you see how in one typical ferromagnetic domain, how many magnetic unit cells are there. Okay. So we need to bother about, when you deal with the neutron scattering, neutron diffraction, magnetic structure, we need to define this magnetic unit cell. For example, if you do X-ray diffraction, what you bother about? The chemical unit cell, ABC, alpha, beta, gamma. So when you do neutron diffraction, of course, you not only get to know about the magnetic unit cell, you also get to know about the chemical unit cell, because if you take this pattern in the paramagnetic phase, you do not get any magnetic atom contribution, means these vectors are all zero. There is no moment at us, because this is a random paramagnetic state. So you get only all atomic positions, okay? Similar, this kind of picture. But at low temperature, you see extra information, that is the moment attached to all these atoms or magnetic atoms, okay? Now, by doing neutron diffraction, what you see here, how this where the magnetic atoms are sitting with respect to this unit cell, whether it is 000 or half 00 and so on. How this magnetic atom is surrounded by other atoms. For example, it is surrounded by nitrogen octahedra. So it is sitting at the center of the nitrogen octahedra, this one iron. Another iron sitting at the carbon octahedra. So then what do you get to know? In this magnetic atom, how much moment is there? So what is the length of this vector? And what is the length of this vector? What is the magnetic moment value? So you see here, this guy is having 5 Bohr magneton, which is at 000. But let us say at the body center, half, what is sitting, that is only 0.8 Bohr magneton. So now you may wonder, as per the Hund's rule, I told you that iron means iron at the same state, oxidation state here. So it should have same amount of moment, but that is not happening. When you put this, may not happen when you put these atoms in a crystalline environment, in atomic environment. Okay. So here moment is high, moment is low. So this is nothing but called high spin state of iron. This is called low spin state of iron, and that comes due to this crystalline electric field from this nitrogen octahedra or carbon octahedra. This is one example you could see that how neutrons are useful to draw this unit cell, which is called the magnetic unit cell. Okay, but it also draws You can also locate all the atoms, whether it is magnetic or non-magnetic. So once you are don't bother about these vectors, it is called chemical unit cell, the building block of a crystalline material. And when you have the magnetic atoms and you put these arrows, means the vector is nothing but the pictorial representation of the moment, dipole moment attached to atoms or ions sitting here. And where those magnetic atoms are sitting, whether 0, 0, 0 or half, 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 and how much moment is attached to that, you can measure those. So you can not only measure the magnetic moment, you also see that I have drawn one vector like this, another vector is also parallel to that. That also comes from this diffraction. It tells me that they are parallel. So that means moments are ferromagnetically coupled. So this is the microscopic picture of the so-called ferromagnetic ordering. When we do DC magnetization or any other bulk technique, we do not have any knowledge about this microscopic, about the atomic length scale information, about the vector orientation of these atomic dipole moments and their magnitude. Okay, so this is one case I gave you. So next day I'll be talking about other few cases, like if there is a ferrimagnetism, just I show you one vector is up, another vector is down, but they are unequal. So you still get net moment because unequal. So on the bulk side, if you do DC magnetization, this kind of material will also behave as if they are parallel, as if, but they are not. They are antiparallel but not fully cancelled. So this is and so on. So I will also show how in a case where they are antiparallel but exactly same. So that is called antiferromagnet. So I will be giving such examples. Intention is to tell you that if you do neutron scattering experiment, if you do neutron diffraction experiment on magnetic material, what novel understanding you have. Okay, and then I will try to correlate their implication in practical applications. So with this, today I like to stop here. So next lecture would be on Friday. That is today's 4th, 6th of this month. That is Friday at 3 p.m. Okay. Thank you.